Okay, so the second half of chapter 2, working with units, we'll mention standardized unit systems. So we can look up U.S. customary system of measurements, either online for a reliable source online or using the textbook, just to get all our standard measurements or a table of our standard measurements and how they relate to each other. In other words, conversion factors that we could build, things like feet, gallon, pounds, and also more uncommon things like fathom, furlong, barrel, things like that. So the problem below involves a mix of units. And in this example, we're given that there's a 20-foot by 40-foot swimming pool. So that's its length on one end and then on one side, so 20 feet wide by 40 feet long. It has lost 0.25 feet or 1/4 of a foot of water from its surface due to evaporation. And I've kind of drawn the picture down here. So this is that pool, sort of tilted up on its side. It's 20 feet wide, so imagine we're looking down into the page at it. It's 40 feet long, and the depth of water that's been lost off the top of this rectangle is 0.25 feet or 1/4 foot. So they ask us in the first question, how many gallons of water have been lost from this pool if this is the case? And they give us a formula to use, that volume is equal to area times height. Remember that volume is measured in something like feet cubed. We're going to need to get it in gallons ultimately. Area is measured in feet squared times feet. And when we look at this, of course, we add these exponents. This is technically a 1 right here. When we multiply these two things, and of course we get cubic feet if we multiply area times height. So this is a bit of why that formula might make sense and how we'll use it. So the first thing we need to do in this problem, they want us to use this formula, V equals A times H, the volume equals area times height formula, to calculate how many gallons of water will have evaporated from this pool if it's lost 0.25 feet from the top of its surface. So looking along here, we're given another conversion factor. This will come in handy a little bit later in the problem. That 7.5 gallons, one volume of measurement, is equal to 1 cubic foot, another measurement of volume. Both are measurements of volume. Now, the first thing we need to do is determine the volume in cubic feet. That's all we've got. That's all we can come up with so far. So we know that the area, in this case, is 20 feet times 40 feet. So that's our area here. Just doing it all together, we could calculate the area separately if we wanted to, but we can calculate within the parentheses there. And then times height, our height h is 0.25 feet. Okay, so feet times feet times feet will be cubic feet. 20 times 40 is 800, and 800 times 1/4 is 200. Of course, a calculator could be handy here, and that's just fine to plug all that into a calculator and come out with it. Again, this is cubic feet, so feet cubed. All right, so that's our volume in cubic feet. Now the issue is we need to get it in gallons. So we'll use our conversion factor, and it's a nice time for the stoichiometry table. So I'll write my 200 cubic feet below, and that's our only given measurement. It's not a rate or anything, so we'll just write it as a fixed amount right here. Extend our division bar. Remember, on either side of the vertical bars, we multiply. Over the long horizontal bar, we divide. So 200 cubic feet, we need that to cancel and leave us with gallons. So I'll put 7.5 gallons in the numerator here. 7.5 gallons, and below that, that is equal to 1 cubic foot. Okay, and it looks like things are set up correctly because the cubic feet will cancel and we'll get gallons. Remember that we'll multiply everything in the numerator, 200 times 7.5, and the only unit left is gallons, and we divide by the product of everything in the bottom, which oftentimes will be pretty easy, just 1 times 1, and we've got 200 times 7.5, and that comes out to 1,500 gallons. Calculator, of course, is a nice way to come up with that. 1,500 gallons. Okay, so the second part of this problem they give us a cost, and they want us to use the rate of a water bill to determine how much it's going to cost to refill the pool back to its original level before it lost that quarter foot of water from the top. So they tell us that water costs 0.125 dollars per 100 gallons. So in other words, that's 12.5 cents per 100 gallons. And they ask, how much will it cost to refill the pool? So we have our rate. We know that the rate is 0.125 per 100 gallons. Okay, so we can make use of this. And well, using unit analysis, we realize we have a number of gallons that have been lost. They're saying how much will it cost? So we know that we want to end up in dollars when we're done canceling these units out. So the unit analysis tells us that we need gallons to cancel, and we need to arrive at dollars. So that informs us how to use this conversion factor that we have right here. This is our essentially a conversion factor slash rate. Or rate. You know, if $0.125 is equal to 100 gallons of water, that's essentially how we would build that conversion factor we have there. So we'll take our 1,500 gallons we have from above. It's the amount of water that was lost. That's what we're going to need to put back into the pool. Over 1, put our stoichiometry table together. And we need gallons to cancel and end up with dollars. So it looks like we have this written exactly as we'd expect. $0.125 per 100 gallons. And this is equal to approximately, once we multiply everything out, 1,500 times 0.125 divided by 100. Maybe I'll write that extra step just to see it. But we'll have, well, first we see that gallons cancel, and that's great. And we're left only with dollars. So that's what we'd hope for. That was our intention. We have 1,500 times 0.125 over 1 times 100. And this, of course, is dollars, the only unit left. And that's equal to approximately exactly $1.875. Of course, it's dollars, so you can put that dollar sign in front. Okay, and we should round that to the nearest cent. It's the most reasonable thing to do in the problem, and we're gonna have to do that quite a bit probably in my lab anyway. So of course, remember, look at the 7. The number to the right is 5 or larger, so we need to round that 7 up to the next number. And so we get 1.88. So always pay attention to how they tell you to round these problems. So $1.88, they didn't tell us to round here, but it's reasonable to do so, and nice practice for when you do have more direction in my lab problems or in the web campus quizzes. So that's the volume of water loss from a pool, the cost of refilling the pool from a rate of charge for the gallon for water use. And the third question they ask is sort of the reverse of question A. So now they say, suppose at some other time the pool has lost 5,000 gallons of water to evaporation. How many inches would the surface level drop? Okay, so we've got a little bit further to go with this one. We've actually got the opposite. 5,000 gallons of water, if we write that down, we realize that that's a volume of water. Gallons measure volumes. So I write 5,000 gallons down, and then I call it V for volume. Okay, and I remember my formula. V is equal to A times H. And we know from the previous page that our area, A, is equal to 20 times 40. This is the same swimming pool. We're still in the same problem. And that was 800 square feet. So that's a useful tool to have, a useful piece of information to have set aside. How many inches would the surface level drop? So how many inches would the surface level drop? That's H. What height does this water change by? What height of water is that to lose that much off the surface? So we're looking for H in this problem, and it turns out we know A and we know V, so that's perfect. We can fill in for V, we can fill in for A, and then we can solve for H, right? And that's exactly how we'll do this. So from below, we've got, well, almost exactly how we'll do this. The first problem we notice before we jump into it, though, is that 5,000 gallons is not, it doesn't relate to 800 square feet. So we have to convert volume in gallons to volume in feet, cubic feet. Gallons to cubic feet. So that's one of the tricks we need to handle first. Okay, and in doing so, we'll write 5,000 gallons down with our stoichiometry table, just so we'll be able to convert this over 1, multiply across vertical bars, divide across horizontal bars. Now 5,000 gallons, and if we remember our conversion, we know that 1 cubic foot is actually approximately equal to 7.5 gallons. It's good enough for us to use that. And what we get from this, we realize that gallons cancel, so we've got things set up correctly. And it's actually 5,000 divided by 7.5, because both of those numbers are times 1 on the top and the bottom, and that's our cubic feet. This is actually exactly equal to, we haven't gotten it to a decimal and rounded it yet. So 5,000 divided by 7.5 in a calculator is 666.6 repeating cubic feet. So I'll just round it to 0.67 for now, cubic feet. And I'll change my equal sign to be approximately equal, to be very careful about how we state things. And this is our volume in cubic feet. And that's what we actually need in our V equals A times H, our volume formula. Okay, so we need this number to have similar units to this number. Okay, and I'll explain one more thing about this as we finish it up. So let's go to this formula now that we've converted volume into cubic feet. So we'll have 666.67 cubic feet. Right, this is our V, and this is equal to area, 800 square feet. This is our A, times an unknown H, right? This is what we're trying to find in this problem. Okay. So we've got it all here, and we just need to solve for H. Well, H is times 800 square feet. If we divide both sides of this equation by 800 square feet, then we'll have solved for H, 800 square feet. Okay, and in doing that, let's see what we'll get on the left-hand side. 666.67 divided by 800 comes out to approximately 0.83 repeating, something like this. And let's write the units down carefully. We divided feet cubed by feet squared. So I'm going to leave those units as is, as a fraction still, and I just want to make sure we see this nicely in this part of the problem. Feet cubed divided by feet squared, and of course this is approximately equal to H. We divided by the number in front of H on both sides. Feet cubed divided by feet squared, well, with exponents, we lose 2 powers here with 1 remaining. Both of these powers cancel to 0, so it's gone. And so we're just left with 0.833 feet. This is exactly what we would expect. So H turns out to be in the correct units, 0.8333 just feet, right? Feet cubed divided by feet squared is feet, and height should be measured in feet anyway. You should always let the units guide you and check to make sure that your answer makes sense and that the units are checking out as well. And that's a good way to catch errors in case they do happen. The last part we have to do, this is our height that the pool will have dropped in terms of water level. We'll have lost 0.833 feet. The problem is they asked for this value in inches at the very top of the problem. Okay, so we have to go back and convert 0.833 feet into inches. It's not hard. We just go back to our stoichiometry table and we'll do the same thing we've always done. Divide over the horizontal bar, multiply over the vertical bars. And we've got 0.833 feet. Remember, it's over 1 if there's no rate or anything. If it's just 1 unit there in feet, which is always divided by 1. And our conversion from feet to inches, we know that there are 12 inches in 1 foot. So things that are equal to each other always fit vertically onto these stoichiometry tables. 0.833 feet times 12 inches over 1 foot. We see that the feet cancel. When we get a calculator to do this multiplication, we have 0.8333 repeating feet times 12, or inches times 12, and we end up with, this actually comes out to 10 inches. Turns out this is exact, but even if we left this with wavy equal sign, that would be just as well. All right, so that's 10 inches that the pool has dropped. And that should make sense to us, especially because we've already done a version of this problem or something similar to it. Remember that over here on the first page, it lost 1,500 gallons down here. And that was after it had dropped by 0.25 feet, which is 3 inches. So 3 inches is less than 10 inches. 1,500 gallons is less than 5,000 gallons, but not by a whole lot. So this answer it's consistent with the work we did in part A. It's always nice to be able to check consistency of your answers with other parts of problems that you might have worked on. Okay, so that's one of the hardest types of problems we'll do. It might be seen as a volcanic ash problem. Level of a lake is a common thing, but in our case, we did it as the level of a pool. You might just be given the area as is. You might not have to calculate it through 20 times 40 equals 800 like we did here. It might just be a known value. Okay, so to come back to something a little easier, we'll get to the metric system. So there are prefixes in the metric system. We usually start with a base unit, a central unit, and that is something like a meter, and then a kilometer or kilogram or kilo anything is 1,000 of those. Seconds, of course, are the same in metric as they are in standard units. And then we have liters for volume as well, which have a translation to cubic centimeters. You can look up those conversion factors. But a little bit more on these prefixes: kilo, mega, giga. The place these are most commonly known is in computers and hard drives, essentially. So 1 byte is essentially a unit of information. A kilobyte is 1,000 bytes. A megabyte is 1,000,000 bytes. So 10 to the 6, this is 10 to the 3rd. A gigabyte is 10 to the 9th. It's 1 trillion bytes, and so on, tera, peta, and so on from there. So that's what's listed down below. Now, going the other way, things can get smaller. We can have a deci, centi, 10 to the -2. And if we remember scientific notation, which we'll practice on the next page, we'll know that when we have 10 to a negative power, our numbers are becoming smaller and smaller decimals. Okay, so just converting these, you can either do a quick sort of inspection or a decimal trick. If you need to, a stoichiometry table is also available for this. So I'll do the first one kind of easily. I have 42.195 kilometers, and it needs to become meters. So for it to become meters, what I might do is just erase kilometers out of my way. And I know that kilometers is 1,000 meters. So I'll move this decimal place, move it 1, 2, 3 units to the right, and this is going to be this many meters. It's 42,195 meters. When it's easy, direct, this is completely efficient. This is a totally fine way to do this problem. 42,195 meters from 42.195 kilometers. Now for gigabytes to kilobytes, this could be a little bit more difficult. Okay, so what we want to do is this. We'll write down what we start with in a stoichiometry table. We'll call it GB for gigabytes. I think we're all somewhat familiar with that. Divided by 1, that's what we're converting here. And draw our vertical bar to divide through. We need to cancel gigabytes. So for each step up here on this list, there are 1,000 kilobytes in a megabyte. There are 1,000 megabytes in a gigabyte. Okay, and that's our key. Every one of these steps in these Latin prefixes is another step, is a factor of 1,000. Okay, so let's write that down below on the table, and this should help. We need gigabytes to go away. In 1 gigabyte, we need it to become smaller. We need it to be a kilobyte. In 1 gigabyte, there are 1,000 megabytes. Okay, similarly, so that leaves us gigabytes canceled. So far, so good. Megabytes remain. We need megabytes to cancel and get the kilobytes. Well, kilobyte is the next step down from megabyte. If we look up here, we see this order across these three. It's kilo, mega, giga. Okay, stepping up by factors of 1,000 for each of those. And down below, we could in turn reverse that. We have 1 megabyte to cancel with the 1,000 megabytes, top left. And in 1 megabyte is 1,000 kilobytes. And we see that megabytes are now gone. We're left with kilobytes. As long as we've set up our numbers correctly in this, we're all set. So 3.25 times 1,000 times 1,000, all divided by 1 times 1 times 1. I'll leave the denominator out. We multiply all those together and get 1, so that's fine. This is times 10 cubed is 1,000. I'll make a note of that up here just so we see it. Okay, times 10 cubed again. Okay, multiplying by 10 is just a matter of moving the decimal place. Multiplying by 10 3 times is moving the decimal place 3 times to the right. Again, it's 3 times to the right as well. So we can carry that out below by just writing 3.25 and then moving 1, 2, 3 for the first 10 cubed, 1, 2, 3 for the second 10 cubed. Anywhere there wasn't a number, we can place zeros to fill in these places, and it looks like we end up with 3,250,000 kilobytes in 3.25 gigabytes. And we should always end with our units. That's what they're asking for. That number doesn't quite fit in the blank above, so I'll just leave it down here boxed up. Okay, so that's our metric system. And this leads us into, since we'll be dealing with powers of 10, it doesn't hurt to have a look again at scientific notation. We'll convert from standard to scientific notation and vice versa. Remember that a number in this form is standard form. A number in this form is in scientific notation. Okay, I'll do the first one. So this is in standard form, and they ask us to convert it to a number in a scientific notation. So to do so, all we really need to do is we start where the decimal place is, and we count up places to the left. 1, 2, 3, 4, 5, 6. We stop when there's only one number to the left of the decimal place. So we've got 6 places to move here, and this is equal to 1.569224, no commas in these decimal places, times we move 6 places, 10 to the 6. And that is this portion. Okay, next, let's go down to part C. I'd like to do this one next because we haven't seen 10 to the 6 just means we're going to take this decimal place and move it 6 times to the left, and we get some number that looks like 2,943,700. And it's not as interesting as possibly a negative exponent down below. So if we have a negative exponent, what we want to do is take 5.555 equal to what we're going to do here, because we'll take this decimal point right here and move it to the place left 5 times. We'll move it 5 places to the left. So in doing so, we have 1, and then anywhere there aren't more numbers, we'll just put zeros in when we're done. 2, 3, 4, 5. So this is 1, 2, 3, 4 zeros to fill in. And our standard notation for this number is this, 5, 5. Okay, so those are 2 of the more important ones to do. Down here, note that this number, when we move this decimal place to the right, however many places we go, it's going to be to a power of 10 to a negative power. In fact, we can do it somewhat quickly. We'll count 1, 2, 3, 4, 5, stopping when there's one number to the left of the decimal place. And we counted 5, so that's 2.5 times 10 to the negative 5. And that's the scientific notation for a number that looks like that, starting with a decimal. I think the one I didn't do is fairly easy. You just move that decimal place to the right 6 times. That's part B, and it's fairly straightforward. Now, simplifying expressions with scientific notation, this might come up from time to time, so let's handle some examples like this. This is the nice thing about this situation. When we're multiplying two numbers in scientific notation, we can multiply the front numbers, the front values, 1.2 times 3, and we can multiply the factors of 10 in their own groups. So that simplifies things a little bit. We can have 1.2 times 3, and then times 10 to the 5th times 10 to the negative 4th. What we're using is the commutative property of multiplication. In other words, we can move products of terms around and it won't affect the overall answer. So we'll get the same thing no matter how we move these things. So we move them to be convenient. 1.2 times 3 is 3.6. Calculator can help with that. 10 to the 5th times 10 to the negative 4th. Remember, when we multiply numbers with exponents, if they have the same base, then we can just carry out that product, and it's 5 plus negative 4. You add their exponents. 5 plus negative 4 is positive 1. So we have 3.6 times 10 to the first power. So this is really just 36. Move that decimal place 1 to the right, and that's how we would end up with 36. So 36 is our answer to this one. And then down below, we can play a very similar game. It's getting more complicated, but again, we can isolate some numbers, 2 times 5, ones that are similar, divided by 4. And we can even do this over a division bar. Now, if there's a plus sign in here, things get a little messier. We probably shouldn't see anything like that, but we have to be a little more careful. There's a plus sign. These are all times each other, so this works out okay. We've got 10 to the 5th times 10 to the 4th, and that's divided by 10 to the 6th. And now 2 times 5 over 4, this actually comes out to 2.5 on the left there. Calculator can help with that. And then 10 to the 5th times 10 to the 4th is 10 to the 9th. Adding 5 and 4, right? We add those exponents, this one and this one add together for that. And it's divided by 10 to the 6th. And that's equal to, well, 2.5. When we have 10 to the 9th over 10 to the 6th, we're going to subtract the powers. So it's 9 minus 6. So 2.5 times 10 to the 9 minus 6. That's a 3 in that exponent. So we get 2.5 times 10 cubed. And that's equal to, well, move the decimal place 3 to the right. So we have 2, 1, 2, 3. So 2,500 is our answer here. 22,500 is the final answer with that one. Simplifying numbers in scientific notation. So that's about as complicated as those we'll get, dividing and multiplying numbers in scientific notation. So one of our most complicated problems in our last one is currency conversions, and we're going to do that with rates. So a very practical problem is this idea that we'll convert overall down here at the bottom, $1.34 Canadian per liter of gasoline. We want to find its price in US dollars per gallon. So that's our goal in all of this, but let's learn some currency conversion before we jump into that final part, C down there. So we assume for this problem that the currency exchange, or the exchange rate for Canadian dollars, CAD, to US dollars is 0.8 US dollars equals 1 Canadian dollar. We'll talk about some interpretation on that when we're done with part B or maybe part A. So with this conversion factor, or this identity right here, we can build a conversion factor as needed. We're asked to convert $8 Canadian to US. We're saying how much is $8 Canadian in US dollars. Okay, so $8 Canadian. What I'll do is just write $8 Canadian like this. This is 8 Canadian dollars. We want to convert it to US dollars. So I'll put a bar here. Anytime we're converting units, we can go to stoichiometry table. Now I want Canadian dollars to cancel out so that I will have US dollars. So I'll put 1 Canadian dollar here, and I'll put 0.8 US dollars here. What I'm using is the conversion factor, or the conversion rate, that's given to me by the problem. Okay, we're assuming that this is the case. And I think I've set this up correctly, or I know I have, because Canadian dollars cancels with Canadian dollars, and we're left to multiply 8 times 0.8, 0.8 Canadian dollars over 1 times 1. Of course, we don't need that detail, but just to, again, remind us that that's what's actually happening. 8 times 0.8 is 6.4 Canadian dollars. We can put the dollar sign in if we like, but CAD stands for Canadian dollars, so we could just leave that as is. Further, so 6.4 Canadian dollars. Let's finish part B, and then we'll go back and talk about that exchange rate in terms of interpretations for stronger dollars and whatnot. Now, how much is 9 US dollars in Canadian? Okay, so similar game, but be careful. Don't just set it up quickly like we did the last one. We want to make sure that we convert 9 US dollars over 1 correctly to Canadian dollars. So what we've seen so far, note that 0.8 US dollars is equal to 1 Canadian dollar. Similarly, 8 Canadian dollars was equal to $6.40. Oh, there's a mistake here. This should be US dollars. Glad we caught that. US dollars, I'll put right here. Again, US dollars as well. Oops, just lost track of units. Now, yeah, so $8 Canadian here was $6.40 US. Okay, which one is the stronger currency, or what do we expect? At least in part B, we're converting 9 US dollars to Canadian dollars. In every case where things have been similarly equal, there are fewer US dollars than Canadian dollars in these situations. 8 to 6.4 and 0.8 US dollars to 1 Canadian dollar. So it should be that we get more Canadian dollars here for our 9 US dollars. Let's see that happen in this calculation. So it looks like Canadian dollars are just larger than US dollars in the sense that if we have 1 Canadian dollar, we have 0.8 US dollars, so on. So just letting us be guided by the following: 0.8 US dollars just to cancel the units. We need US dollars to cancel. That's all we really need to use here. We don't even need to think about really any of what I talked about. It's just an idea of what we expect our answer to look like. But setting up the stoichiometry table, everything is the same. 1 Canadian dollar, we have US dollars over US dollars. It's going to leave Canadian dollars. It's exactly what we expect, what we're trying to get. And we end up with 9 times 1. 9 times 1 over 1 times 0.8. Of course, that's 9 over 0.8, and this is Canadian dollars. Canadian dollars. And that is equal to 9 over 0.8 Canadian dollars. And in the end, this is, with a calculator in hand, we get a value of, it's like 11.25 Canadian dollars. That might be rounded, might be approximated, so we'll just put wavy equal sign just in case. Okay, of course, the calculator helps us to come up with that. So yeah, as expected, 11.25 Canadian dollars is a larger number than the 9 US dollars. And that's been the case for all of these. So things are at least consistent with what we've done. 8 Canadian dollars came out to 6.4 US dollars. So then the Canadian number was larger than the US number. Now the question is this: which dollar is stronger, the US dollar or the Canadian dollar in this case? And it's tempting to say it's the Canadian dollar because there are 8 of them that are equal to 6.4 US dollars. But let's think about it this way. What you can buy for 8 Canadian dollars only costs you 6.4 US dollars. So it looks like the US dollar in this situation is stronger, and that in fact is the case. Again, let's look at it maybe in this situation, in the exchange rate itself. 0.8, it only cost 80 cents US to buy something that's $1 Canadian. So if it takes one currency a less amount than another currency to purchase the same thing, or for them to be equivalent to each other, then the currency with the lower number, in this case 0.8, is the stronger currency to the one that takes the full dollar to do that. Okay, so that's how we measure strength in currency, which one's weaker or stronger than another. Our last problem is sort of our apex problem for the whole chapter, and that's to convert a rate from $1.34 Canadian per liter to US dollars per gallon for gasoline. Okay, so we'll start with, we have $1, maybe I'll leave the dollar signs off again, 134 Canadian dollars. And now we have a rate, it's per 1 liter. So I can put per liter, or I'll put 1 liter per 1 liter of gasoline. That's the way gasoline is sold in Canada. So we're given a conversion factor that's going to be very helpful. 3.7 liters is 1 gallon. So let's go ahead and use that one right now. It's right in front of us. We'll use it. We'll have 3.7 liters. And the game here is always the same. We want these units to cancel across that division bar, that horizontal division bar. This is 1 gallon. So we're going to end up with per gallon. But as is, we have Canadian dollars per gallon. Okay, so we need the Canadian dollars to convert as well. Of course, we could do this in steps, but this table really helps us check all our information, put it all together in one shot, multiply everything along the numerator, multiply everything along the denominator, and then divide numerator over denominator. And we'll see that before we finish this. So to convert Canadian dollars to US, we'll need 0.8 US dollars in the numerator, is one of our multiples up top, divided by 1 Canadian dollar. So Canadian dollars will cancel, and US dollars per gallon is what we're left with. And that's exactly what we're looking for in terms of this conversion. Now the denominator is fairly simple. It's one of those lucky ones again. It's all ones. So 1 times 1 times 1 is just 1. That's fine. We have $1, or 134 times 3.7 times 0.8, all divided by 1, and we have US dollars in the numerator per gallon, and we'll find that the unit we end up with is US dollars per gallon, and that's exactly what our intention was. And our number here, approximately in a calculator, 1.34 times 3.7 times 0.8 is roughly 3.9669, I believe, US dollars per gallon. And well, we need to round this to the nearest cent to make it a little bit more reasonable. Most likely, most problems will ask for that. So it turns out that it's 3.97 US dollars per gallon. This would be really handy if we were driving to Canada and we were crossing the border or going to cross the border, happened to know what the price of gas there was, and wanted to compare that to buying gas while you're still in the United States. It's nice to be able to make a smart, informed decision about your expenditures. So that's it. That is the hardest problem we should see in this chapter, is that rate, and the volume problems are probably close to that as well. Note there are some extra problems to do in the notes. Take some time, work through these in detail. They're going to be very similar to the exercises we did, and they're a great introduction from the notes into the actual problems you have to do in MyLab. So good luck with these, and see you in the next video.